Good morning, class. I hope everyone is having a great day. Today, I would like to look over the worksheet titled How Fast with you. And at the top of this worksheet, we have a position versus time graph. So our independent variable is time, so that is placed on the x-axis. Our dependent variable is position, so that belongs on the y-axis. At the top of your paper, you have several ordered pairs here, and I've identified the last ordered pair, which is 6:24. So our x value is 6 seconds, and our y value is 24 meters. So there are 13 questions on this assignment, and I would like to work these out with you. Okay? So for number one, it wants to know what is the formula for delta t. Well, remember that the Greek letter delta, right here, this symbol delta, represents change in. And so the change in time, our time interval, is equal to the final time minus the initial time. So t sub f minus t sub I. Number two, it wants us to calculate the time interval when the object is at a position of 8 meters and moves to a position of 24 meters. So what we're going to do here is take a look at our position time graph. We're first going to locate a position of 8 meters. And so we're going to take a look at the y-axis on our position time graph. So we have 8 meters right here. And we need to identify the time when we're at a position of 8 meters, and that's 2 seconds, okay? 24 meters, right here, we are at a time of 6 seconds. So to calculate the time interval, delta t, we're going to use this base equation, t sub f minus t sub I. My final time is 6 seconds. 6 seconds minus our initial time of 2 seconds. So delta t is equal to 4 seconds. And please remember to write down the units because the units are half of the answer. Number three, what is the formula for the change in displacement? So remember, we have our Greek letter delta representing change in. Lowercase d, this is displacement. And so delta d is equal to the final position minus the initial position. So d sub f minus d sub I. Now in number four, it wants us to calculate the change in the object's displacement from 1 second to 6 seconds. So at 1 second, right here, let's identify our position. So we're at 4 meters here. And I'll just come over here. So 4 meters. And then at 6 seconds, well, we've already identified that. That's 24 meters. So what we're going to do is delta d is equal to final position minus initial position. This is going to equal 24 meters minus 4 meters. So our change in displacement is going to be a positive 20 meters. Okay? All right, let's move on to number 5. On number 5, the question wants us to identify the formula for the slope of a line when we have a linear relationship. Now we know slope is identified by lowercase n. And we know this is the rise over the run. So delta y divided by delta x. And I'm going to expand the numerator and the denominator here. So I have change in y is y2 minus y1 divided by the change in x, x2 minus x1. Okay? Now it wants us to calculate the slope in number 6. So slope identified by lowercase m, y2 minus y1 divided by x2 minus x1. So y2 This is going to be 24 meters minus, and we want to use the most extreme points here. So y1, or our y-intercept here, is going to be 0 meters. In my denominator, x2, I have 6 seconds, minus x1. Right here, we're starting out at 0 seconds. So I have 24 meters divided by 6 seconds. So the slope is equal to 4 meters per second. Okay, so calculate the slope. M is equal to 4 meters per second. All right, let's take a look at the slope. Now, number 7, it wants to know what is the absolute value of the slope on the position time graph. Well, the absolute value is speed. So, the absolute value of the slope on a position time graph is equal to speed. Now, speed is a scalar quantity. It is not a vector because it does not show direction. Okay? So it's just representing magnitude. Number 8, it wants us to calculate the velocity of the object. Well, we've actually already done this here. Okay? So the velocity of an object is the slope of the line on a position time graph. So our velocity, identified by lowercase b, is equal to 4 meters per second. Okay? On number 9, how long does it take to reach 150 meters? Okay? So we're going to use the equation, the change in an object's displacement, delta d, is equal to the average velocity multiplied by the time interval. Okay? So how long? So this indicates time. So what we're going to do is isolate our variable delta t here. And we're going to do this by dividing by average velocity on both sides of the equal sign. So I have delta t is equal to the change in displacement divided by v bar. So our average velocity, change in displacement, is 150 meters. Okay? Our average velocity, so the velocity of our object, is 4 meters per second. So go ahead and get your calculator out. 150 divided by 4 is going to give me 37.5. Now let's take a look at the units here. Here, I'm going to erase some of this. So, taking a look at our units. In my numerator, I have meters. In my denominator, I have meters over seconds. So, algebraically, we can write meters as meter over 1. We're dividing this by meters per second. And let's remember the old algebra rule that says whenever we divide fractions, it's like multiplying by the inverse of the denominator. So what we have is meters over 1 times seconds over meters. Okay? So our meters are going to cancel, leaving us with units of seconds. And we know that this is correct because time is in units of seconds. Okay? So the answer to number 9, how long to reach 150 meters, is 37.5 seconds. Okay. And number 10, what is the change in displacement at 200 seconds? Okay, so now they are giving us a time, and we're going to use this base equation. So delta D is equal to our velocity, And so our velocity is still 4 meters per second. Our change in time right here is 200 seconds. And 4 times 200 is 800. So delta D is equal to 800. But now let's take a look at our units. So units, we have meters per second times seconds. And we can write that as seconds over 1. Right here, our units of seconds are going to cancel out, leaving us with units of meters. So the change in the object's displacement is 800 meters. So delta D equals 800 meters. Okay? Now, on number 11, it wants us to write down or identify the formula for final displacement of an object. Now, earlier I mentioned our equation for the change in displacement, delta D, is equal to our average velocity multiplied by our time interval. But what we want to do here is identify final displacement. So let's go ahead and expand the left side of the equal sign. Remember, delta represents change in, so the change in displacement. This is the final displacement minus the initial displacement. And we actually did that in number 3 already. This is going to equal our average velocity multiplied by our time interval. Now, what we want to do is actually get rid of our initial displacement. And on the left-hand side, we're subtracting initial displacement, so we need to do the opposite operation, which is going to be add initial displacement to both sides. So my equation is going to be d sub f equals v bar delta t plus d sub I. That is our equation for final displacement of an object. So right here, v bar delta t plus d sub I. So let's just go through this equation real quick. D sub f is the final displacement of the object. V bar represents average velocity. Delta t represents time interval. And d sub I represents initial displacement of the object. Okay, so on number 12, they want us to calculate the final displacement of the object when the initial displacement is 180 meters. So that means the object is 180 meters from the origin. It's going to have a velocity of 2.5 meters per second, and we have a time interval of 48 seconds. So I'm going to go ahead and write down my base equation. We have v sub f equals v bar delta t plus d sub I. Okay? My average velocity is 2.5 meters per second. My time interval is 48 seconds. And we're going to add our initial displacement of 180 meters. Okay, let's go ahead and take out our calculator. So according to the order of operations, we're going to multiply first right here. So 2.5 meters per second times 48 seconds. This gives me 120. Okay, and let's take a look at our units. We have meters per second times seconds, which we could say seconds over 1. Our units of seconds are going to cancel, leaving us with units of meters. And then we have to add our initial displacement here. Remember that our object is now starting 180 meters away from our origin. Okay? So we have 120 meters plus 180 meters. And the question I want to ask you here is, can we add these together? Well, we can add them together because we have the same units. Units of meters and units of meters. So 120 plus 180 meters is going to give us 300 meters. And that is our final displacement. Okay, so let me write this down, 300 meters. Now in number 13, the last question, it has a grid set up there for you so you can graph number 12. So that's what I would like to do right now. So I'm going to erase this. Now what we want to sketch is a position time graph. Since both of my values for time and position are positive, we're going to be in the first quadrant. So time in units of seconds, and we have position in units of meters. So let's generate a scale here. Our maximum time is 48 seconds, so we're starting at 0. 48 seconds, and then we have 24. It's going to be 36. This guy is going to be 12. Okay, so that's a decent scale on the x-axis. And on the y-axis, our position, our maximum value is 300. So that's 150, 150. Okay, all right. So I've got a scale on my y-axis. Now in number 12, our initial position is 180 meters. So let's go ahead and graph that. So at time 0, right here, time 0, my position is 180 meters. So let's go ahead and place that ordered pair there. At a time of 48 seconds, my position is 300 meters. Okay. There we go. All right. So on your graph on number 13, you should have something that looks similar to this. Okay. Well, I hope this has helped. If you have any questions over this worksheet, or we've talked about scalars and vectors, the difference between the two. We've also discussed the difference between distance and displacement, and a couple of formulas that we've gone over today. If you have any questions, please send me an email. I hope you have a wonderful day.